So what we're going to discuss here is the turning point. We did a couple examples today in class for showing you what happens when an object gets to a point and turns around and goes the other way. This is like the cart on the ramp as it rolled up the hill. You can see time zeros down there at the bottom. And so these are the motions of the cart all the way to the top of the ramp. And we know when we get to the top of the ramp, at the top of the ramp here, we know the velocity becomes zero due to the fact that it does stop. The object works its way back down, getting faster and faster to the bottom. To show where the acceleration is, either on the way up or the way down, we just need to pick 2 points. Accelerations are VF minus VO. So as long as you subtract 2 vectors, a starting one and an ending one, that are in sync with each other, so the first and the second, third and the fourth, you can find out where the acceleration is pointing. I would pick this point and this point as my beginning and end. I'll just subtract VF, which is the top one, minus VO. That means same magnitude, opposite direction, which will give me a change in velocity downwards. Remember, accelerations always point towards the change in V, so on the way up the ramp, you're losing velocity because your acceleration is backwards. On the way down the ramp, if I select this point and this point as my starting and ending points, I can see that my VF minus VO, the change in velocity, is still down the hill. The reason there's a change in velocity down the hill is that I'm now picking up speed. On the way up, the acceleration was down the hill, and on the way down, the acceleration was on the hill. But the main point that we wanted to focus on here is right here, the turning point. What happens when you reach that max peak? You can see right before the peak, velocity is heading up the hill, and right after that peak, the velocity is heading down the hill. Starting velocity would be this one, and my ending velocity would be that one. So if I take a VF minus VO again, the final speed is down the hill. Minus VO is taking that first vector and flipping it, which is also down the hill. The change of velocity there is from start to finish. At that point, change in velocity is down the hill. So it means even at the highest peak, right here, I have zero velocity, but I do have an acceleration at the turning point. If I didn't have an acceleration, the object would reach that highest point and just stop. To find something's instantaneous velocity, you need to take the derivative of its position with respect to time, which means you are getting a slope of the line of a very small segment in x over a very small segment in time. What I mean by that is if you look at this graph, you've got 3 points that they're focusing on. T1, you can see they took the slope right around that 2.5 second mark and gives you a certain instantaneous velocity. If you look at T2, that slope becomes a little bit higher because now we're taking the slope of that tiny piece at 4.5. And at time 3, you can see the slope becomes even higher, so the derivative would show a much higher slope for position 3. So if I plot those 3 points that they had for T1, T2, and T3, T1 would have a velocity here, T2 would have a velocity here, and T3 would have a velocity here, showing my velocity is increasing as time goes on. I can connect those points with a line. That shows me now is that I have a constant increasing velocity. My position time graph was a parabola, and now my velocity time graph is a straight line. What this means is that if I take the slope of this line, or the derivative of this line, is the change in velocity over time, which we now know is the acceleration. The acceleration graph can be created from taking derivatives or slopes of this velocity graph. Taking the slope of this, that line is constant, would give you an acceleration graph points here, here, and here. Drawing a line through those points gives me a nice flat line, so our acceleration versus time here is a constant acceleration at whatever that value is, whether it's positive acceleration, negative acceleration, all depends on what scenario you're coming up with. And just like we showed you in the train example, that if you have a velocity time graph, what you can find with the area under that curve is how far the object travels. So if the area is above the x-axis, you'd have positive displacements. And if the area is below the x-axis, you'd have negative displacement. The most important thing out of this is that we can get all of the information we ever need off of a velocity time graph. Velocity time graphs are the most important graphs you'll ever see in mechanics because they give us so much information. If this line here was flat, I would know instantly that that's constant velocity. My position graph should be increasing steadily, and I should have no acceleration. For this graph, I see a positive slope, meaning that I am positively accelerating throughout the entire trip. So if I wanted to write some equations for this line, we could look at the slope first. The slope of the line tells me a change in velocity over a change in time, which we defined as acceleration. If I stretch this formula out, Vf minus Vo, I'm going to bring that t over and give you acceleration times time. And if I want to solve for final velocity, which we've already written out and shown this formula before. So this right here, I get from the slope of a velocity time graph. If I want to find the final speed at any moment, I can get the initial speed plus acceleration times time, solve for whatever I'm looking for there. Or we said that something really important here is the area under a graph. If I look at this area under the curve, I actually have two shapes here. I've got a rectangle, and I've got this triangle. Adding these two areas will give me the total area under the curve. The total area under the curve here, since it's a velocity time graph, I know this all has to give me displacement. If I do the geometry on each of those, the easy one first is the rectangle. So I could write my displacement would equal my height of the rectangle, which is VO, times the length of my triangle, which is time. And I'm going to add that to the area of the triangle above. So that would be 1/2 times the base is time, times the height. Now the height here goes from this flat line all the way up to here, which we could call our final speed. So if I wanted the height of that triangle, really what I'm looking for is the change in velocity. So there is a second equation I can have. But from what we know before, I can define a change in velocity as an acceleration. And that change in velocity, remember, has to happen over a certain amount of time. Change in velocity actually can just be acceleration times time. And I can throw that up into this equation above. If I wanted to stretch this out, my change in position would be my initial speed times time plus 1/2 multiplied by acceleration times time, or as we like to write it, acceleration times time squared. Crunch out the units for yourself, do the unit analysis, show me in the notes you can prove that the units here of VOT plus 1/2 AT squared have to cancel out to give you meters in the end. So prove that to me. One change on this graph could be that the object starts from rest, meaning that it has no velocity in the beginning. So all that would change is that my orange line here would start at the origin, which all that would do to my equation would make VOT disappear. When deriving these formulas, you may not have a term based on where your graph started. If it has a y-intercept of 0, that means it had no speed in the beginning. Okay, so using our first equation we got from the slope of the line, that VF equals VO plus AT, we can also use distance equals the average velocity times time. From what we talked about with average velocity, we can rearrange that and solve that our displacement would equal our average velocity times time. But if I was changing my velocity, a way to calculate an average, like if you had two people and you had an average height, would be to take the starting velocity and the final velocity and just divide those two in half. So really I could expand that right side of the equation to be displacement is VO plus VF over 2 times time. first two problems I gave you, if you wanted to solve for anything, you had to time the problem. But if you forgot to time the problem, you had at least three measurements, maybe a distance, a starting speed, an ending speed. You've got to have three variables when solving for any of these equations. With this, since they both have time as a factor, I can solve both of them for time. So I can have time equals the change in velocity over acceleration. And on this side, I can have time equal to 2 times the displacement over the addition of the two velocities. And since I have two equations now that are solving for time, what I can do is combine both times and combine these equations together. That'll end up giving you is VF minus VO over A equals 2 delta X over VO plus VF. Just doing some rearranging and cross multiplication here, you'll end up with 2 acceleration times displacement, and on the other side you're going to have to multiply VO plus VF and VF minus VO. So when trying to do that, you're going to have to do your foiling where you do your first outer and inner, and what you're going to end up with here is a VF squared minus a VO squared. Rearranging this again so that we don't have any minus signs in there, I can say that the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration multiplied by the displacement. So in that third equation there, I don't need time at all. I need to know how far you went, I need to know your acceleration, starting or an ending speed, and I should be able to solve for whatever is missing. Again, just like we did before, I'm going to ask you in your notes to prove the units. Prove to me that these units all match up and make sense with each other.